In this video, we're going to look at two numerical methods techniques. The first one's called the mid-ordinate rule, and the second one's called Simpson's rule. And both of these techniques are similar to the trapezium rule in the way that essentially we're going to approximate the area underneath a curve. Okay, so if you look at the diagram, we know already from the trapezium rule there are our ordinates, so x0, x1, x2, x3, and the key is in the title. We do not actually use these ordinates, we use the mid-ordinates. And it's actually quite a simple approximation, this one, compared to some of the other techniques. So what we do is, if we had like x0 to x1, we'd use x 0.5. And we don't sub in x0 and x1, we sub in x of 0.5 into our function, and that would give us out the corresponding y value. Y of 0.5. And literally all this does is it approximates that strip as a rectangle. So remember, the notation on this is h. H stands for the width of each of our strips, just like it did on the trapezium rule. And we just sub in the value in between, in the middle. That gives us the height of our rectangle, and h is just the width of our rectangle. So similarly for this one, if we were going between x1 and x2, we'd be using x 1.5. We'd substitute that into our function. That gives the height of our rectangle. And then we'd approximate this area just as a rectangle, like this. And obviously the last one, between x2 and x3, we'd use x 2.5, substitute that in to get the height, the y value, and we'd approximate that as a rectangle. Okay, so it's quite a basic approximation this, but obviously if we wanted to get more accurate, we could just reduce the value of h if we use more strips. If you cut it up into loads of tiny little strips, as h approaches 0, this would still accurately approximate this area that underneath our curve. One thing to be careful of, just to really clarify, right, you do not use the original ordinates. Don't sub in x0, x1, you sub in the mid-ordinate, because all we need to figure out is the height. Okay, and the formula that we're going to look at in a second, which you do get in the formula booklet, it's just basically adding up all these rectangles. So you've got all your mid-y values, multiply them all by h, and it's just a simple way of calculating this area for us. Okay, so let's try an example. It says, use a mid-ordinate rule with 5 strips of equal width to approximate the integral. And obviously, like, don't forget, we are approximating this, we're not integrating this. So all we need to do is figure out our y values and sub them into the formula. You just want to be careful here. You can do it on the graphical calculator. I'll show you in a second. It's nice to put it into a table as well. So if you've got your x values, x0, x1, x2, x3, and x4. Now if you think about it, I suppose the first thing we should calculate is like the width of our strip. It should be obvious, like if you're going from 0 to 5 and you're using 5 strips, clearly h is going to equal 1 in this question, isn't it? So what's your x naught? X naught would be 0, but remember we don't sub that in, like that's, if you want to visualize this, like if you start at 0, whatever the function looks like, and then the next one would be at 1, but we want to sub in 0.5, because remember we're trying to get this rectangle, so we're always using the mid-ordinate, we don't use the actual original ordinate. So x1 would equal 1, x2 would equal 2, x3 would equal 3, x4 would equal 4, and x5 would equal 5. So we're actually going to sub in 0.5, 1.5, 2.5, 3.5, and 4.5. that's a coincidence that the 3.5 matches up with the 3.5. Like that has only happened because we're going from 0 to 5 and we're using these ordinates here. Okay, that will not usually happen. So just to make it clear, this is what we're going to be using. So when we go to do it on the calculator, remember the table function. So if we go on to table and then enter the function, which is the square root of 100 minus 4x squared, execute, and then set. We are not starting at 0, we're starting at 0.5. We are ending at 4.5. And the step, how much we go up by, is the value of h. So we're going up by 1 each time. Okay. And then press table. And we get our y values, which is what we need to sum into our formula. Remember what I was saying about this last time? The calculator doesn't round these properly, so just be careful. See the way it's 9/8, it's 9/87. So just make sure you scroll across these values to get accurate values. All right. So then I would say that the area is approximately equal to h, which is just 1. And then we add up our y values. You might want to write the y values out as well in the table. But I'm just going to, as long as you show the method and clearly show each of these y values, you will get your method marks. Okay, so we want to be accurate to 3 significant figures. Should have highlighted that, it's easy to forget. Just make sure we use more accuracy than that in our working out. Okay, so it'll be 9.94, 987 plus 9.53. 939 plus 8.66025. Nine eight nine, so I'll keep going. 9 9. I should have really wrote 90 there, but it doesn't really matter. Okay, so let me just tidy this up and we'll see what we end up with. Okay, so once I've done this, I'm getting 39.6498 to 3 significant figures. I did also, just to check that my working was correct, I actually evaluated this in school on the calculator. So if we integrate, remember you can do this using, so if you press math and then F6 to scroll across, you can input the integral here. And the calculator, it actually, when I did this, it spat out an exact answer, which I was surprised about. It'll be some sort of trick substitution that we can use. Let's see if I can get it to do it again. Yeah, so it gives it 25 over 2 pi, okay? But if we turn that into a decimal, we can see that the calculator is telling us it's 39.269. You got 39.6. Like, it's not a brilliant estimate, but don't forget, literally all we've done is chopped it up into 5 rectangles, 5 strips, so we used 5 rectangles. If you wanted to make it more accurate, you could just use more strips, okay? After we've maybe practiced a couple of these, but then we'll look at the next technique, which is called Simpson's rule. Simpson's rule is the other technique that we're going to look at, and there's a little bit more going on with this one. I'm not going to attempt to draw like how this one works. In the exam, you don't need to know this. Like you could be asked to draw the mid-ordinate rule in terms of like drawing the rectangles, but Simpson's rule is essentially it approximates the curve as parabolas, and obviously the smaller the strips, the more accurate the parabola would be. But you don't need to draw these ones for our exam, thankfully. Okay, let's just try an example. It says use Simpson's rule with 5 ordinates to approximate this integral. Okay, we could start by figuring out what h is. So we're going from 9 to 1, so it'll be 9 minus 1. Remember, we divide by the number of strips. Now if you've got 5 ordinates, don't forget that what that really means is you've got like 5 x values, x0, x1, x2, x3. So if we had 5 values that we were subbing in, we'd only have 4 strips. So we'll divide by 4. And we're going to be increasing in 2s. Okay? The only place you can really go wrong on this formula is just make sure you start with x0. Like if anyone's going to go wrong, sometimes people will start with x1. The initial ordinates, just label that one x0. So for this one we're starting at 1. We're going up in 2s, so x1 would equal 3, x2 would equal 5, x3 would equal 7, and x4 would equal 9. So we've got 1, 2, 3, 4, we've got 5 ordinates, and we're going from 1 to 9. So we know we've done this correctly. The way I think about this is the first and the last. See y0 and yn. So n is just the last value. First y value, last y value, we just count them once. The odd ones, so y1, y3, y5, if you kept on going, you count those 4 times, and the evens, which in this case is actually only going to be x2, which will give us y2, is going to be counted twice. Okay, so y1, y2, y4. Oops. Don't do what I just did. Start with 0, y1, y2, y3, and y4. The pattern that we're going to be using is 1, 4, 2, 4, 1, because the first and last count once, the odds count 4 times, and the evens count twice. If you would have had, like, say for example, if there would have been 7 ordinates, then the pattern would still start and end with 1, and then it'd be 1, 4, 2, 4, 2, 4, 1. First and last always count once. Then the odds, which is y1, y3, y5, and the evens, y2, y4, would be counted twice. But I mean, as long as you label this correctly, start with x0, and sub them in the right place, you should be fine. Okay. So let's use the table function on the calculator again. The function that we're working with this time is 1 over 1 plus root x. Okay. Oops. Let me go back. Set. So we're going to start with our first value of 1, end at 9. And we're going up in 2s each time. Got this one. Okay, so we're getting 0.5, 0.3, 6, 6, 0.25, 0.3, 0.9, 0.7. And 0.25. Okay, so once we've got these values, we can then sub them into the formula and say that the area is approximately equal to 1/3 of h, which is 2. Open up a big bracket, because we'll all be multiplying by this. 0.5 plus 0.25, first and last. And then we do 4 lots of y1 and y3. And 2 lots of the evens. In this case, it's only y2. Okay, obviously just be careful, make sure we use the correct y0 notation. So first and last, 4 lots of these, 2 lots of these. In terms of the marks in the exam, this could be like a 4-mark question, maybe a 5-mark question. If you show this method here with the correct correct values, you've got the vast majority of the marks. The last mark is just for evaluating this on the calculator. Let's see what we get. Hope you can see that. I subbed them in times by 2/3 at the end, and I'm getting 2.6195. So to 3 significant figures, 2.62. And if we actually check, I typed in the in-school as well. So if you evaluate the in-school on the calculator, it's 2.613, which is really accurate, isn't it? If you think about it, like we're accurate, almost accurate to 2 decimal places. You know, we're accurate to 1 decimal place, and all we've done is split it up using 5 strips. And if we wanted to make it more accurate, we could just use more strips, so reduce how much we increase by each time. All right, thanks guys.